Hey there, everyone. So this is the third video of section 1.4. Here I actually just want to go over a couple interesting examples that will help sort of shed a little more light on what's going on and how everything ties together. I think these will also be good examples to go over as they will sort of provide a good foundation for types of problems that you yourselves will be doing both on homework, quizzes, tests, and whatnot. So, first example, we've got this matrix A equal to 1, 3, 4, negative 4, 2, negative 6, negative 3, negative 2, negative 7, and B. And notice here I've defined B to be just a vector B1, B2, B3. So B is not fixed, it's just some vector of length 3, we don't know what it is. And what we want to do here is describe all possible B1, B2, B3 for which the matrix equation AX equals B is consistent. And of course, remember consistent here implies that this matrix equation has at least one solution. So when I say describe all possible B1, B2, B3, and you'll see this, this type of question pop up a bit this semester, or during this class, what we want is we want some relationship on these variables, like some sort of constraint or requirement on these variables that will make this consistent. I think when we work through it and we see the solution we get and we talk about it, you'll see a little more what we mean by describe. In a way, you can almost think of it as asking for like the domain of B1, B2, B3 that make this consistent. That is, we want to find some sort of like way of describing all of the numbers that I can assign to these three values that will result in a consistent equation. So remember, what we learned is that the solution to any matrix equation that looks like this can be found by just taking the augmented matrix and row reducing. And so here we're going to use, again, this trick that where we row reduce with variables, where notice B1, B2, B3 in our row reduction algorithm will never actually play too big a role in what we're doing. When I row reduce, I'm only going to pick potentially these three elements as pivots. And so I'll sort of just row reduce, adding and subtracting B1, B2, B3 with each other as necessary in order to put this matrix in reduced row echelon form. And the goal will be, when I have this matrix in reduced row echelon form, to look at all of the possible B1, B2, B3 values that I could get and try and figure out when is this going to be consistent and not consistent. So going forward with the row reduction algorithm, I think the first thing I want to do, well, I want to use this 1 to clear out its column, so I'm going to do 4 row 1 plus row 2. And so notice in the last column, I just get a 4b1 plus b2. And so at the same time, I'm going to do 3 row 1 plus row 3. So I'm also going to clear out this negative 3 in the same step here. Doing that, of course, I get a 0 in the first column. 3 times 3 is 9, minus 2 is 7. All right, 4 times 3 is 12. Minus 7 is 5. And then here I get 3b1 plus b3. All right. So next thing, well, you might immediately notice actually, so now I'm going to make this 14 a pivot. So this is going to be my next pivot entry in my row reduced echelon form matrix. Again, it's going to correspond to a leading one eventually. But notice here, I don't want to divide through by 14 because 10 isn't divisible by 14, and I tend to only want to divide through to make that a leading one, right off the bat, again, if every element in the row is divisible. But I noticed that I can get rid of that 7 by just doing negative 1/2 row 2 plus row 3. And something here very interesting happens. Well, I get a 0 there, which I was trying to do. I wasn't necessarily trying to get a 0 here, but I get a 0 here. Here I don't get 0. I get 3b1 plus b3 minus 1/2 times 4b1 plus b2. Bit of a long entry there, but it's okay. And so notice here, at this step, I actually now have enough information to be able to tell when this is going to be consistent and inconsistent. So if you want to convince yourself and you want to keep row reducing these last 2 rows, you can. These last 2 rows will row reduce where I get a leading one here and a leading one here. And remember, row reducing, if we get like a leading one and any number, those variables are fixed. And those rows really won't have anything to, those rows won't have much of an impact in making the system not consistent, right? If I get a leading one here, it's going to fix the value of x1. If I get a leading one here, it'll sort of fix the value of x2. This last row is now the only thing that really concerns me. Because notice I've got 0x1, 0x2, 0x3, and this big polynomial here. And so specifically, whenever this big polynomial is not equal to 0, well, we're going to have issues, right? Because if this big polynomial is not equal to 0, then I get the dreaded 0, 0, 0, 0, 0 non-zero entry row. So as long as, and I'll do a little bit of reducing here, so notice I can kind of combine like terms. I get 3b1 minus 2b1, so b1 minus 1/2 b2 plus b3 is equal to 0, then ax equals b is consistent. But notice, if that polynomial is not consistent, or sorry, if this polynomial is not 0, then the system is inconsistent. And so otherwise, ax equals b is inconsistent. And so, of course, this equaling 0 leaves me a lot of leeway, right? I only have to satisfy one relation on b1, b2, b3. But I can now describe all possible vectors which make this system consistent because every vector, b1, b2, b3, has to satisfy this inequality. Right? Because the row of all zeros is fine. That gives us a free variable, and we can always find a solution with a free variable, right? In that case, we'll get infinitely many solutions to this matrix equation. But if I get a non-zero entry here, it'll be inconsistent. All right, so I want to do one more problem. This will sort of be applying theorem 4, which I introduced at the end of the last video. And remember, theorem 4 had that long list of things that were equivalent. And so I want to sort of use that knowledge to look at a type of question you might get asked that sort of continues the trend of solving the same problem asked in a variety of different ways. So this is number 22 in your book. And so I can write out the problem here. So we're going to let v1 be the following vector of length 3, 0, 0, negative 2. We're going to let v2 be the vector 0, negative 3, 8. And we're going to let v3 be the vector 4, negative 1, negative 5. And so the question is, does the set v1, v2, v3 span R3. All right, so remember what it means for a set of vectors to span R3. So remember, this means that for any vector we'll say for any vector b in R3, b can be written as a linear combination of these three vectors here, if I choose the right set of weights or scalars to multiply those vectors by, right? So saying that this set of vectors spans R3 is just by definition saying that, well, if I take any vector of length 3, I can combine these three vectors in the right way to sort of get to this vector b. All right, so remember that this is one of the conditions of Theorem 4, right, that says all of these four conditions are equivalent. One of the equivalent conditions is saying, well, this set of vectors spans R3. So what Theorem 4 tells us, remember Theorem 4 wasn't immediately talking about a set of vectors, right? It was talking about the columns from a matrix A, right? So it's saying, well, the columns of A span Rm, right, is equivalent to being able to row reduce A and getting a pivot position in every row. So if I want to figure out, do these three vectors span R3, maybe what I'll do is I'll define a matrix A whose columns are just these three vectors. Right, so notice now I've just defined a matrix A whose column 1 is V1, column 2 is V2, column 3 is V3. And so what Theorem 4 tells me is that if I row reduce A and give a pivot in every row, that is, get a leading 1 in every row, then the columns of A span R3. So these three vectors would span R3. So what I want to do is row reduce A. So doing this, A is in a sort of odd, a bit of an odd place at the moment. First thing I'm going to do is swap row 1 with row 3, right? Because I want to get a non-zero pivot in the first top left entry here, and the only non-zero entry in all of my rows is this -2 here. What I'm also not going to do quite yet, I don't want to make that to a -1 quite yet, again, because the -5 there isn't divisible by 2. And this 4 being here is going to help me a lot. So notice by just doing that row swap, I've already completed the first couple steps of putting this matrix into reduced row echelon form, because everything below this 2 is 0, everything below the -3 is 0. So what I can do now is do 1/4 times row 3, turn that 4 into a 1. And I can start using this 1 to eliminate entries above it. So here I'm going to do row 3 plus row 2 and replace row 2. And then I'll do -5 row 3 plus row 1 and replace row 1. So notice that these steps together zero out all of the entries above this 1. All right, now what I can do is, well, I want to make this -301 and this -201, so I'll do -1/3 row 2, row 2, and -1/2 row 1. Make that matrix. And now it's just one more step, and I've got this in reduced row echelon form. And I get the following matrix doing that. So we'll actually see this exact matrix a lot later on. A preview, this is called the identity matrix. What is significant about this matrix? Well, notice it's got a pivot in every row, right? So every single row in A, I can find a pivot. Specifically, when I, sort of an equivalent way to say that is that when I reduce, I get a leading one in every row, which I get here. That means that V1, V1, V2, V3 spans R3. And so again, this is what Theorem 4 tells us. Sort of some intuitive reason why I had promised a little bit of that previously. Notice here, when I get so notice this was not an augmented matrix corresponding to, right, adding a vector B onto it. This was just row reducing the coefficient matrix. But remember, whenever I row reduce like with an augmented matrix where I've added that extra vector B, I'm never using any of the entries in B as a pivot, right? That's one of the big things that, if you're going to get a solution, you don't want to wind up with an entry in your last column of your augmented matrix as a pivot. And so if you can imagine all of these steps being done with some vector B attached onto the end, I would actually get the exact same first three columns here in my row reduced echelon form with just some set of numbers there. And what would always happen then is that this would correspond to a fixed solution no matter what vector B I added to the end, right? And so what this is saying is that the matrix equation AX equals B always has a solution, which, as we learned, is equivalent to saying this set of vectors spans R3. That is, this vector equation also always has a solution. And so, again, sort of this idea of row reducing and getting this sort of being able to always guarantee that you get some fixed assignment for every variable no matter what is a good thing, right? Because I'm never going to get a row of all zeros that tends to give me trouble where I might not get a solution. All right, so that wraps up section 1.4. So be on the lookout if it's not already posted for the 1.5 lectures.